Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight, we'll drift together through the spiralling arms of something enormous and ancient, the Milky Way galaxy, our home among the stars. But this won't be a race through facts or a rapid-fire science lesson. Instead, it's a slow, starlit walk through wonder, a story of dust, darkness, and everything in between. From ancient myths to cosmic rays, from satellite eyes watching Earth to the silence of alien skies. But before we settle in and begin this calm journey together, I'd be ever so grateful if you could take a moment to gently press the like button, subscribe if you'd like to visit this sleepy universe again, or just leave a comment letting me know where in the world you're listening from, and what time it is for you right now. It's always a quiet joy to see the little constellations we form, scattered across the planet, all tuning in together beneath our shared stars. Maybe you're lying in bed, blanket pulled just under your chin. Maybe you're curled into a corner of the couch, or letting this play softly as you unwind after a long day. However you arrived, you're here now, and that's enough. If you like, you can dim the lights. Maybe turn on a fan for that gentle hum in the background. Let the world grow quiet around you. There's no need to take notes or remember every detail. This isn't a lecture. It's a gentle unfolding, like the spiral of the galaxy itself, looping and drifting through ideas, stories, and strange, beautiful facts. Some of it may surprise you. Some of it may feel familiar, like the echo of something you already knew but had forgotten how to name. You'll learn how ancient people looked up and saw a milky river across the sky, not realizing they were gazing at the light of hundreds of billions of stars. You'll hear how scientists mapped that river, measured its heart, and even discovered that it's not alone, not even close. The universe is brimming with galaxies, each one a dance of gravity, dust, and light. We'll dive into the centre of our own galaxy, where a quiet monster, a supermassive black hole, waits behind veils of gas and mystery. You'll also hear stories of storms we can't see, cosmic rays flying through the galaxy at nearly the speed of light, some of them striking you as you listen, like invisible whispers from exploding stars. And then, the strange question. Why haven't we heard from anyone else out there? The Milky Way may be teeming with planets, with oceans, with possibilities, and yet it's so very quiet. We'll explore what that might mean. Maybe life is rare, or maybe it's common but cautious, or maybe we just haven't learned how to listen yet. And finally, we'll come home. We'll look at Earth, not from ground level, but from space, from the view of satellites and astronauts, a blue speck in a black sea. You'll hear about the Landsat missions and how we use space to understand ourselves, and you'll hear about the overview effect, a term for what happens to the human mind when it sees the Earth from above. Small, whole, alive. That's the shape of our journey tonight. One spiral, one galaxy, one home, and if, somewhere along the way, your thoughts begin to drift, that's perfectly fine. Let them. That's part of the design. You don't have to stay awake to learn something here. You just have to let go a little, like dust settling in starlight. So now, take one more breath. Let your shoulders drop. Let your eyes rest. The spiral is waiting. Let's begin. Long before telescopes and satellites, before physics and photons, before even the written word, there were people. And those people looked up at the night sky. What they saw was something both ordinary and unexplainable. A pale, misty band stretching across the heavens. Not quite a cloud, not quite a line of stars. It was soft and smoky, faint but impossible to ignore. To those early stargazers, it looked like a river, an ethereal stream flowing across the dome of the night. In ancient Greece, they gave it a name that would echo through time, Galaxius Kyklos, the Milky Circle. The myth behind it is as vivid and strange as any you'll hear tonight. According to legend, the infant Heracles, son of Zeus, was brought to the goddess Hera while she slept. He suckled at her breast, and when she awoke to find the child of another woman feeding from her, she pulled away in shock. Her milk sprayed across the heavens, forming the celestial streak we now call the Milky Way. It's an origin story not grounded in science, but in symbol. Human emotion cast onto the stars. Other cultures told their own stories. In ancient China, the Milky Way was known as the Silver River, a celestial waterway separating the weaver girl and the cowherd, two lovers exiled to opposite sides of the sky, allowed to meet only once a year. The bridge they cross is formed by birds, a trail of stars in the shape of longing. The Inca too saw a river in the sky, connected to the flow of water on Earth, mirroring their own rivers and reflecting the cycle of life, agriculture, and ancestry. The Khoisan people of southern Africa spoke of it as the ash trail left behind by a girl who tossed embers into the sky, lighting her way through the dark. In every story, the band of light became a thread, of milk, of water, of fire, binding earth and sky in a single line of mystery. These myths weren't attempts to get the science right. They were attempts to find meaning. The sky wasn't just a dome filled with objects. It was a living canvas, and the Milky Way was one of its grandest brushstrokes. But time passed, and stories began to shift. In the Islamic Golden Age, scholars like al-Sufi catalogued the stars and gave early descriptions of nebulae, including the luminous band of the Milky Way. He described it not as milk or smoke, but as a cluster of countless small, tightly packed stars, too faint to be seen individually. The poetic haze, it turned out, might be real. Still, it wasn't until the early 1600s, when an Italian mathematician named Galileo Galilei raised a telescope to the sky, that the illusion truly began to unravel. Galileo pointed his simple device, a tube of lenses barely stronger than a pair of modern binoculars, at that familiar streak. What he saw was astonishing. The hazy ribbon was not a mist at all, but a dense collection of innumerable stars. It was as if the sky, long thought to be smooth and perfect, had been found textured and teeming. Millions of stars packed so tightly together that from our place on Earth, their light blurred into a luminous fog. This discovery didn't just change astronomy. It changed the scale of everything. The night sky was no longer a flat dome studded with jewels. It was deep, full, swarming with stars. Galileo's observations, written down in trembling Latin, didn't claim to understand everything, but they cracked open the sky. And once opened, it could never be closed again. Later, astronomers would follow where he led. They began to count, to map, to wonder. What was this river of stars? Was it flat or spherical? Was the sun at its centre or somewhere else entirely? It would take another 2 centuries before these questions began to be answered. William Herschel, working in the late 1700s, decided to count stars. He and his sister Caroline used telescopes to record the number of stars in different parts of the sky. Their results suggested something startling. The stars weren't evenly spread. Instead, they seemed to cluster in a flattened shape, a disk. And within that disk, the sun appeared to be, well, somewhere near the middle. It was the best guess at the time, a rough outline, a sketch drawn with data and uncertainty. But still, it was progress. Herschel's disk was, in many ways, the first scientific map of the Milky Way. Of course, it was also wrong in one important respect. The sun isn't near the centre. It's offset by about 27,000 light-years, a figure discovered later by Harlow Shapley, who studied clusters of stars called globular clusters. He noticed that these clusters formed a sphere, a halo, and that the centre of this distribution was far from where Herschel had placed the sun. This told astronomers something humbling. We are not at the centre of the galaxy. In fact, we're off to the side. A bit player in a much larger drama. The river of milk had become a river of stars, then a spinning disk, then a system with structure, motion, and a place for us that was not the centre, but still connected to everything. And even now, when you step outside and look up, if you're lucky enough to be far from city lights, you can see it. That same faint band. It's easy to forget what it really is. Hundreds of billions of stars stretching in a spiral around a common core viewed from within. You're inside it, and outside it too. Watching and belonging. It's difficult, perhaps even impossible, to imagine what it felt like to be Galileo Galilei in the winter of 1609, standing in the dark with a crude telescope, peering into a night sky that, until then, had only ever been understood with the naked eye. The telescope was not his invention, but his improvements to it, including enhancing its magnification power, made it something more than a novelty. It became a key, and that key would unlock a sky that had, for all of human memory, been locked by simplicity and assumption. Galileo's telescope was humble by modern standards. Its lenses were ground by hand, its field of view narrow, its images blurred at the edges. But what it offered was something far more profound than clarity, perspective. When he pointed it at the moon, he saw craters and mountains, imperfections in what had long been assumed to be a flawless celestial sphere. When he turned it toward Jupiter, he saw moons, tiny moving dots that orbited the gas giant, evidence that not everything in the cosmos revolved around Earth. But then, one night, Galileo turned his instrument toward the Milky Way, that familiar faint band across the sky. What had always appeared as a continuous smear, like a celestial brushstroke of white dust, suddenly resolved itself into its true nature. The haze was not haze at all, but a dense congregation of stars, thousands upon thousands of them, too many to count, each one a tiny point of light that, until now, had been swallowed in the glow of their collective brilliance. In his notes, Galileo wrote that the Milky Way was nothing but a congeries of innumerable stars grouped together in clusters. It was a plain sentence, but an extraordinary one. For the first time, a human being had seen the Milky Way for what it truly was. A sprawling stellar system, not a trick of the atmosphere, not a mystical pathway for the gods, but a structure, vast and real, composed of stars like our own sun. That moment marked a quiet but radical shift. It wasn't just that the Milky Way was made of stars, it was that the universe was bigger, deeper, and more populated than anyone had imagined. What had once seemed decorative became architectural. The night sky was not a ceiling, it was a space, and Galileo had peered into its depth. In the decades and centuries that followed, other astronomers built upon this revelation. With each new instrument, with each improvement in glass and grinding and gear, the sky revealed a little more. Telescopes became stronger, clearer, and more stable. The language of light became something we could begin to translate. But alongside the technological progress, there was also something more abstract unfolding, a reshaping of humanity's place in the cosmos. If the Milky Way was made of stars, and if those stars were suns, and if our own sun was just one of them, then what was Earth, really? A single planet orbiting a single star, inside a single galaxy, among an unknown number of others. The implications were dizzying. In 1750, English astronomer Thomas Wright proposed that the Milky Way's band of stars, the reason it appeared as a flat streak in the sky, was because we were viewing the flattened body of a rotating system of stars from within, like being inside a disk and looking through the dense edge rather than the open face. It was speculation, but it nudged thought in the right direction. Then came William Herschel. He didn't just theorise, he measured. Along with his sister Caroline, Herschel undertook a star-counting survey, dividing the sky into hundreds of segments and tallying the stars visible through his telescope in each one. From the number of stars and their apparent distribution, he sketched a rough map of the galaxy, a flattened lens-shaped structure, wider than it was tall. In this early version, the Sun sat near the centre, because from his vantage point, the count seemed roughly symmetrical. He didn't yet know about interstellar dust, which blocks our view of the more distant parts of the galaxy, and creates the illusion of evenness. Still, the work was foundational. For the first time, someone had drawn the shape of the Milky Way. Not mythically, not poetically, but with numbers. Caroline Herschel, often working in the cold, moonlit hours beside her brother, made discoveries of her own. Comets, star clusters, and deep sky objects that hinted at a universe far more complex than anyone had guessed. Their collaboration, quiet and methodical, brought the sky into sharper focus, and their maps, while imperfect, revealed a cosmos that was no longer centred around us. It would take decades more before this decentralisation became fact. Harlow Shapley, using variable stars called Cepheids, showed that the centre of our galaxy wasn't where we thought. He studied globular clusters, dense collections of ancient stars orbiting the Milky Way, and noticed they formed a spherical distribution offset from the Sun's position. This suggested the true galactic centre was tens of thousands of light-year away, in the direction of the constellation Sagittarius. Once again, the cosmos had nudged us off-centre. There is a quiet humility in this unfolding. Each generation of observers looked a little deeper, understood a little more, and with each revelation, the Earth, and by extension humanity, grew smaller in the cosmic map. But the shrinking was not a loss. It was an expansion of perspective. As our size diminished, our understanding grew. And there's something deeply comforting in that balance. A trade of scale for insight. Tonight, if the sky is clear and dark enough, you can look up and see the same band of light that Galileo saw. Your eyes, unassisted, will see only a misty streak. But now you know what it truly is. Not a cloud, not a milk trail, but a river of suns, each one a point of possibility, each one a silent echo of that moment in 1609, when a man in Italy lifted a tube of glass to the sky and saw for the first time the crowd of stars that had always been waiting. Measuring the size of the Milky Way, and our place within it, has never been simple. You can't stretch a tape measure across light years. You can't take a photo from above. And until relatively recently, you couldn't even be certain that what you were looking at was a single object. The Milky Way, after all, surrounds us. We are inside it, like fish trying. To map the ocean, our perspective is limited by immersion. But human beings, even when surrounded by mystery, have always found ways to reach beyond their limits. And the story of how we measured the galaxy is one of persistence, pattern, and a bit of well-timed luck. To understand distances in space, astronomers first needed a kind of celestial lighthouse, something that could signal, "I am this far away," using the language of light alone. Fortunately, nature provided one, flickering steadily in the dark. That beacon came in the form of Cepheid variable stars. Discovered in the late 19th century, Cepheids are pulsating stars. Stars whose brightness changes over time in a predictable rhythm. They grow brighter and dimmer, expanding and contracting like beating hearts. What makes them so special is not just the pulse itself, but the relationship between the period of their brightness change and their intrinsic luminosity. In other words, by measuring how fast a Cepheid pulses, you can tell how bright it really is, not just how bright it looks from Earth. This critical discovery came thanks to Henrietta Swan Leavitt, a computer at the Harvard College Observatory, back when that word referred to people, not machines. In the early 1900s, Leavitt was cataloguing variable stars in the Magellanic Clouds, two nearby galaxies visible from the southern hemisphere. She noticed that the brighter Cepheids had longer periods of pulsation, and the fainter ones had shorter ones. By plotting this relationship, she provided astronomy with a cosmic yardstick. That yardstick changed everything. Because once you know how bright something should be, you can compare it to how bright it appears and calculate how far away it is. The difference between the two tells you the distance. The farther a star is, the dimmer it appears. It's a trick of light and math, and it opened up the universe. Leavitt never won awards in her lifetime, and much of her work was overlooked at the time. But today, her discovery is recognised as one of the foundational insights of modern astronomy. Armed with Cepheids, astronomers began to measure. One of them was Harlow Shapley, working in the early 20th century. Shapley turned his attention to globular clusters, spherical groupings of hundreds of thousands of old stars that orbit the Milky Way like bees around a hive. These clusters aren't scattered randomly. They tend to form a halo around the centre of the galaxy. And in many of them, Shapley found Cepheid variables. By using Leavitt's method, he calculated the distance to each cluster. What he discovered was profound. The centre of this spherical distribution was not where the Sun was. It was somewhere else, far off in the direction of the constellation Sagittarius. That meant the true centre of the Milky Way was not where previous maps had placed it. The Sun was not in the middle. We were off to the side in one of the spiral arms circling the centre like a distant outpost. This revelation did more than redraw our galactic address. It rewrote our sense of importance. Once again, as with the Copernican revolution centuries earlier, humanity had to let go of the idea of being central. First, we lost our place at the centre of the solar system. Now we had to relinquish the centre of the galaxy too. It was humbling, but also liberating. The realisation that we were not central, but connected. As the 20th century progressed, astronomers continued refining their tools. They discovered that Cepheids weren't the only stars that could serve as distance indicators. Other types of variable stars, supernovae, and even red giants could be used to measure space. Still, the fundamental idea remained the same: brightness as a clue to distance. But there was another complication, a kind of invisible fog that dulled our view. Between stars lies not empty space, but interstellar dust. This dust absorbs and scatters light, especially in the visible spectrum, making distant stars appear dimmer than they really are. For decades, this cosmic smog made the galaxy look smaller than it was. Many early distance measurements underestimated true distances because they didn't account for the dimming caused by dust. As a result, early maps of the Milky Way were distorted, like trying to map a landscape while peering through smoke. Eventually, astronomers learned how to correct for this by using different wavelengths of light, particularly infrared, which can pass through dust more easily. They began to see more clearly. What once seemed like an opaque wall of shadow opened up into a structured spiral. Our galaxy, it turned out, was a vast disk, about 100,000 light-years across, with billions upon billions of stars, and we, the Earth and Sun and everything we know, orbit in a minor spiral arm called the Orion Spur, not at the centre, not at the edge, but somewhere between, like a quiet suburb far from the bright lights of the galactic downtown. In recent years, the Gaia spacecraft, launched by the European Space Agency, has taken this mapping to an entirely new level. Gaia is creating a three-dimensional map of the Milky Way by measuring the positions and motions of over 1 billion stars with stunning precision. This isn't just a picture, it's a moving, dynamic model of the galaxy's structure and history. With Gaia, we can trace the paths of stars, identify ancient collisions, and even reconstruct the galactic past. We've come a long way from Leavitt's notebook and Shapley's star clusters, but the principle remains the same. Light, measured carefully, reveals distance. Distance, mapped precisely, reveals structure. And structure, understood deeply, tells us a story of how galaxies form, evolve, and carry us within their arms. So when you look at the stars tonight, remember, you are not simply looking up. You are looking across light years, across billions of stars, across the wide measured arms of the Milky Way, where distance is no longer just mystery but memory written in light. For centuries, the Milky Way was not just the galaxy, it was the universe. From the vantage point of Earth, with no way to see beyond its dusty edge, there was little reason to believe otherwise. Even after Galileo's revelations and Herschel's tentative mappings, most astronomers assumed the cosmos began and ended within the foggy confines of our home galaxy. What else could there be? The Milky Way was vast, full of stars and surrounded by only the faintest of ghostly smudges, wisps of light that could easily be dismissed as curious nebulae, nearby gas clouds or star clusters tucked within the galactic halo. That was the accepted view. But then came the 20th century, and with it, the unravelling of an illusion so large that it redefined not just astronomy, but humanity's place in the cosmos. And at the heart of that revelation stood a quiet, unassuming object, the Andromeda Nebula. The Andromeda Nebula had been known since ancient times. Even in modestly dark skies, it can be seen with the naked eye, a faint blur in the constellation Andromeda, just above the northern horizon in autumn skies. For generations, it was catalogued as a nebula, much like the Orion Nebula, or the Dumbbell Nebula, something gaseous, local, maybe even still forming stars. But its light hinted at something else. There was structure in it, a kind of spiralling, a brightness toward the centre, an elongation not typical of nearby star clouds. In the early 1900s, a growing number of astronomers began to wonder whether some of these nebulae were not inside the Milky Way at all. Perhaps they were, in fact, island universes, a term first floated by Immanuel Kant more than a century earlier. These mysterious spirals might be entire galaxies in their own right, floating unimaginably far away. But without a reliable way to measure their distances, the debate remained heated and unresolved. That is, until Edwin Hubble brought light to bear on the problem, both literally and figuratively. Hubble, working at Mount Wilson Observatory in California, had access to the Hooker telescope, the most powerful telescope in the world at the time. Using this 100-inch marvel, he studied the Andromeda Nebula in painstaking detail. He searched its hazy light for Cepheid variable stars, the very kind that Henrietta Leavitt had shown could act as cosmic distance markers. It was a careful, tedious process, one requiring precise photographic plates, detailed analysis, and endless nights of observation. But eventually he found them. Those pulsing stars told a stunning truth. Andromeda was far too distant to lie within the Milky Way. It wasn't a nearby nebula. It was another galaxy entirely, one as vast as our own, filled with billions of stars spiralling quietly in the dark. With that discovery, the Milky Way's monopoly collapsed. The universe was no longer a single spinning island. It was an archipelago, a sea of galaxies drifting apart in a cosmic ocean. Andromeda was just the beginning. Hubble and others soon confirmed that many of the spiral and elliptical nebulae observed in the night sky were in fact galaxies. What had seemed like scattered puffs of light were actually immense structures, star cities glowing across time. But Hubble didn't stop with identity. He also wanted to know something deeper. Were these galaxies stationary, or were they moving? To answer this, he examined their spectra, the unique fingerprint of light emitted by their stars. When light from a galaxy is passed through a prism, it breaks into lines, each corresponding to specific elements. But those lines shift if the source of light is moving. If a galaxy is approaching, its lines shift toward blue. If it's receding, they shift toward red, a phenomenon known as redshift. What Hubble found was astonishing. Nearly every galaxy he measured was redshifted. They were all moving away from us, not just in a chaotic scatter, but in a pattern. The farther away a galaxy was, the faster it seemed to be receding. This relationship, now known as Hubble's Law, implied something profound. The universe itself was expanding. It wasn't that galaxies were flying away from a central explosion like debris from a bomb. Rather, space itself was stretching, carrying galaxies along with it. Like raisins moving apart in rising dough, the fabric of the cosmos was expanding in every direction. This idea that the universe had once been smaller, denser and hotter led directly to the theory we now call the Big Bang. But even before the name took hold, the implications were clear. The universe had a history. It had a beginning. It was growing, evolving, changing. The Milky Way, once thought to be the whole of everything, was now just one galaxy among billions, and perhaps more. The observable universe became a kind of bubble, nearly 93 billion light-years across, filled with star systems, black holes, quasars and dust, all of it held together, or perhaps flung apart by the invisible tensions of gravity and expansion. And so, in the span of a few decades, the known cosmos went from local to limitless. What Galileo saw as a fog became a disk. What Herschel drew as a flattened lens became a spiral. And what Hubble measured as a blur became a universe of galaxies, each one a silent lighthouse shining across time. But here's the most remarkable part. That shift didn't erase the Milky Way's importance. It recontextualized it. We weren't central anymore, but we weren't insignificant either. We were a thread in a vast tapestry, a swirl among swirls, a question mark in a story still unfolding. Tonight, if you step outside and look toward Andromeda, that faint blur above the treetops, you won't see its stars. They're too far away for the naked eye, but what you're seeing is not just light, it's distance, it's motion. It's the echo of a discovery that made the universe bigger than anyone ever dared to dream. When you look up at the stars on a clear, moonless night, it's easy to imagine them scattered across a vast three-dimensional sky, glowing points spread in every direction, as if randomly tossed into the heavens. But when seen through the lens of astronomy, that glittering randomness resolves into structure, not just clusters and alignments, but a sweeping organized whole, the Milky Way, a spiral galaxy, turning slowly in the darkness. And in that great spiral we live, not in the centre, not at the edge, but somewhere quietly in between. The Milky Way is what astronomers call a barred spiral galaxy, a flattened disk of stars, gas and dust, with arms that curl outward from a bright central bulge, like petals or the streams of a pinwheel. At the very core is a dense, elongated bar of stars, a structure that influences how material flows within the galaxy, guiding gas inward and helping to feed the central black hole. From this bar extend the spiral arms, vast rivers of starlight stretching tens of thousands of light-years, weaving in and out like gently uncoiling ribbons. These spiral arms are not fixed structures, like the arms of a spinning wheel. Rather, they are regions of density waves, ripples in the galactic disk where gas and stars slow down and pile up slightly, creating a kind of cosmic traffic jam. As gas clouds enter these denser regions, they get compressed, and in that compression, stars are born. This is why spiral arms shine with young, bright stars, often surrounded by glowing nebulae, the soft red glow of hydrogen gas ionized by newborn suns. The Milky Way has several major arms: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the outer arm, among others. But nestled between two of these larger structures lies a smaller, less grand segment, a spur, really, known as the Orion arm, or Orion Spur. It isn't large enough to be called a full arm, and it doesn't span the galaxy. It's just a minor branch, but it happens to be home. The Sun, along with Earth, and every memory you've ever made sits inside this Orion Spur, about 27,000 light-years from the galactic centre. From our location, We look inward and see the thicker, denser star fields of the galaxy's core, the source of that luminous band we call the Milky Way. When we look outward, toward the edge of the galaxy, the stars thin out, but the view is still filled with beauty, other spiral arms, distant clusters, and the dark voids where interstellar dust blocks the light. If you could rise above the Milky Way and look down from a vantage point 100,000 light-years high, the view would be breathtaking. A softly glowing disk, perhaps 100,000 to 120,000 light-years across, with the central bulge glowing like a candle's core and arms sweeping around it in slow, graceful arcs. In this grand structure, the Sun orbits the galactic centre once every 225 to 250 million years. A galactic year, sometimes called a cosmic year. That means the dinosaurs were just emerging on Earth the last time we completed a single lap. But our position isn't just about coordinates and orbits, it also carries meaning. We're not too close to the centre, where stars are densely packed, radiation levels are higher, and gravitational chaos makes planetary systems less stable. Nor are we at the extreme edge, where stellar density thins to the point of isolation, and the material needed for planet formation becomes scarce. We exist in a kind of galactic suburb, not especially flashy but remarkably stable. A good neighbourhood for life. This position allows us to see much of the galaxy around us. It also allows for the long-term calm required for biology to unfold, one tiny mutation at a time, across billions of years. In more crowded regions, supernovae might bathe nearby systems in deadly radiation. Close gravitational encounters might disrupt planetary orbits. But in this quiet stretch of spiral arm, conditions have remained, if not constant, then at least survivable. Understanding the structure of the galaxy has been like assembling a puzzle from the inside. We cannot step outside the Milky Way to photograph it directly. Every image you've seen of the full Milky Way is either an artist's conception or a model built from indirect measurements. The real data comes from many years of observing stellar motions, gas clouds, and parallax shifts. It comes from infrared and radio maps, from Gaia's exquisite positional data, from tracing hydrogen emissions and counting variable stars. It is a picture drawn not with a camera, but with patience, theory, and deep time. And that picture continues to evolve. Recent observations suggest the Milky Way may not be as symmetric as once thought. Some spiral arms are more prominent than others. There are ripples in the disk, waves that may be echoes of past collisions with smaller galaxies. The halo that surrounds the galaxy, filled with ancient stars and globular clusters, is not a perfect sphere, but lumpy, uneven, a record of long-ago mergers. Even the disk itself is not flat. It's warped, slightly twisted like a vinyl record left in the sun. No one is entirely sure why. It could be the pull of nearby galaxies. It could be a relic of cosmic turbulence. Whatever the cause, it adds to the sense that the Milky Way, while graceful from afar, is also a dynamic and evolving structure, full of subtle imperfections that make it all the more real. We live in one tiny thread of this spiral, a swirl of stars among 100 billion more, and yet from this modest perch we've come to map the galaxy, to name its parts, and to imagine its shape. We've found our way within it, even though we cannot leave it. So when you next look at the night sky, remember, you're seeing the inside of a spiral. You're orbiting within a structure so vast that it takes hundreds of millions of years to complete a single turn. You're riding a wave of stars drifting through arms that curl and shine, drawn ever inward by gravity and outward by the longing to understand. In the direction of the constellation Sagittarius, where the night sky seems thickest with stars, where the hazy streak of the Milky Way glows brightest, there lies something we cannot see. Not because it isn't there, and not because our instruments aren't good enough, but because, by its very nature, it hides. It pulls in light, bends time, and conceals itself behind curtains of dust and gas, and yet it shapes the galaxy around it with silent certainty. At the heart of the Milky Way sits a supermassive black hole, a dark gravitational anchor known as Sagittarius, a star. For most of human history, the idea of such a thing would have seemed absurd. A place where matter collapses into near nothingness, a region from which even light cannot escape. These were not thoughts you entertained when considering the sky. Even Einstein, whose equations predicted the possibility of such objects, was skeptical that they could actually exist. But mathematics, patient and indifferent to disbelief, had already planted the seeds. And the universe, it turns out, is more than willing to grow strange things. Sagittarius A star is enormous. Current estimates place its mass at about 4 million times that of the Sun. But despite this unimaginable weight, it occupies a space no larger than our solar system. A gravity well this deep exerts profound influence over its surroundings. And yet, for much of history, that influence went unnoticed. That's because the black hole is shrouded in clouds of interstellar gas and dust, completely opaque in visible light. You cannot see it with an optical telescope. To observe it, you must shift your vision into the realm of radio waves and infrared light, wavelengths that can penetrate the murk. In the 1930s, astronomers first noticed something unusual in the direction of Sagittarius, a bright source of radio emission that didn't quite match anything else. Over the decades, better instruments narrowed down the signal, refining its location, until it became clear that something extraordinary lay at the very centre of our galaxy. That something was Sagittarius A star, the asterisk in this case, denoting an exceptional radio source, a kind of cosmic footnote whose meaning would only become clearer with time. But even radio waves only hinted at the source. What confirmed its identity, and what truly brought it into the realm of real, measurable science, was the motion of the stars around it. In the late 1990s and early 2000s, two teams of astronomers, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, began using powerful infrared telescopes to track the positions of individual stars near the galactic centre. They watched as these stars moved over time, tracing out tight, fast orbits around. Nothing. No visible object, no source of light, and yet the gravitational pull required to whip these stars around at such speeds could only belong to one thing: a supermassive black hole. One star in particular, known as S2, completed a full orbit around this invisible point every 16 years. That orbit, observed and calculated with exquisite precision, gave astronomers a way to determine the mass of the central object, and what they found matched the predictions of a black hole almost exactly. There was no other plausible explanation. Sagittarius A star was real. The galaxy had a heart, and it was dark. But it wasn't loud. Unlike the black holes at the centre of some other galaxies, the kind that power quasars and active galactic nuclei, unleashing torrents of energy and blazing like beacons across the universe. Sagittarius. A star is relatively quiet. It's not devouring stars wholesale or emitting vast jets of radiation. It's resting, dormant, like a fire that once roared but now smoulders beneath the ashes. Material still falls into it, occasionally triggering brief flares of X-rays or radio waves, but these are whispers compared to the howling engines of more active galactic cores. There's something almost poetic about that. The centre of our galaxy is not a place of violence and fury, but of silence and concealment. A massive presence that does not announce itself, but instead sits patiently, letting its gravity do the speaking. Every star in the galaxy, including our Sun, orbits around this hidden colossus. It binds the Milky Way together, not visibly, not audibly, but fundamentally. In 2022, the Event Horizon Telescope, the same global collaboration that imaged the black hole in the galaxy M87, revealed the first direct image of Sagittarius A star. The result was blurry, distorted, as expected, but unmistakable. A glowing ring of radiation surrounding a dark central shadow. That shadow was the event horizon, the point beyond which nothing returns. The image matched predictions. It confirmed not just the presence of the black hole, but the precision of Einstein's general relativity in a place where space-time is warped nearly beyond comprehension. Yet despite this stunning confirmation, the feeling it left behind wasn't one of fear or drama. It was instead one of quiet awe, that such a thing exists, hidden, massive, central, and yet so completely undetectable to the naked eye. It humbles you. It reshapes your idea of presence. What else might exist all around us, unseen but profoundly influential? And so we live our lives, orbiting gently in a spiral galaxy that turns around a black hole we'll never see. A giant that slumbers at the heart of everything. A silence that holds the stars in place. A mystery so perfectly quiet it lets the galaxy sing around it. Stars are not simply points of light scattered across the sky. They are storytellers. Each star carries within it a record of time, place, and history. A glowing archive of the galaxy's past. When we study where stars are born, how old they are, what they're made of, and where they travel, we begin to read the narrative of the Milky Way itself, the slow, sprawling saga of birth, life, death, and renewal on a galactic scale. The Milky Way's stellar population is not uniform. Instead, stars group into broad categories based on their age, chemical makeup, and location. This differentiation helps astronomers piece together the evolutionary timeline of the galaxy. At the core, nestled in the galactic bulge, reside the oldest stars. These stars are generally redder and cooler, having exhausted much of their hydrogen fuel over billions of years. They formed in the early phases of the Milky Way's formation, when the galaxy was more compact and chaotic. Their chemical signatures reflect the pristine conditions of a young universe. Low in metals, the astrophysical term for elements heavier than hydrogen and helium. These ancient stars are like the galaxy's elders, the relics of its infancy. Moving outward into the spiral arms, you encounter a younger, bluer stellar population. These stars shine brightly with energy, burning hot and fast. They're often found in star-forming regions, dense clouds of gas and dust where gravity compresses material until nuclear fusion ignites. Here, nebulae glow softly, bathed in ultraviolet light from newborn suns. This is the Milky Way's vibrant nursery, a place of constant creation. Between the bulge and the arms lies the galactic disk, a region populated by stars of intermediate age and composition. The Sun itself belongs to this category, a relatively young star at about 4.6 billion years old, rich in metals forged by countless generations of predecessors. This metallicity, the abundance of elements like carbon, oxygen, iron and calcium, is a critical clue to a star's heritage. Stars born earlier in the galaxy's history lacked these metals, as they had not yet been synthesized in previous supernovae and distributed into the interstellar medium. Beyond the disk, enveloping the galaxy, stretches the halo, a vast diffuse sphere populated by globular clusters and ancient stars. These clusters, tight balls of hundreds of thousands of stars, are some of the oldest known objects in the galaxy, dating back to nearly the formation of the Milky Way itself. They orbit the galactic centre in complex, often highly elliptical paths, evidence of a tumultuous early history marked by mergers and accretion of smaller galaxies. What can all this tell us about time? Quite a lot. Firstly, the chemical fingerprints of stars serve as cosmic clocks. Because elements heavier than helium are produced in the cores of massive stars and dispersed by supernovae, their abundance indicates how many generations of stars have come before. By measuring metallicity, astronomers estimate the age of star populations and reconstruct the timeline of star formation across the galaxy. Secondly, the distribution of star ages and motions helps us understand the dynamic evolution of the Milky Way. Younger stars tend to follow the gentle rotation of the galactic disk, moving in near-circular orbits. Older stars, especially those in the halo, move in more erratic, elliptical paths, remnants of ancient collisions that sent them scattering. One striking discovery has been the identification of stellar streams, long, thin ribbons of stars that arc through the halo, relics of dwarf galaxies and star clusters torn apart by the Milky Way's gravity. These streams are fingerprints of the galaxy's cannibalistic past, signs that the Milky Way grows by merging and absorbing smaller neighbours. The life cycle of stars themselves offers a meditation on time. Massive stars blaze brightly but briefly, living only millions of years before exploding in brilliant supernovae that seed the cosmos with new elements. Smaller stars, like our Sun, burn steadily for billions of years, and some dim stars, as red dwarfs, may persist for trillions of years, outliving even the current age of the universe. In this ongoing stellar symphony, death fuels creation. The ashes of exploded stars enrich the interstellar gas, enabling new stars and planets to form. The Milky Way is thus a galactic ecosystem, where matter cycles through stars and space, shaped by gravity and nuclear fusion. For us, this means that the atoms in your body, the calcium in your bones, the iron in your blood, were forged in the hearts of ancient stars that lived and died long before the Earth existed. You are quite literally stardust. When you gaze at the night sky, the stars you see are a mixture of these generations, some born in the last few million years, others hundreds of millions or billions of years old. Each star a marker of time, a point of light tracing the slow, majestic history of the galaxy. And thanks to missions like Gaia, we can now watch stars move in exquisite detail, tracking their orbits and velocities. This data is like watching the galaxy breathe, slow, steady, alive. So, stars are not just lights in the sky, they are storytellers, historians, and timekeepers. Their positions, colours and motions offer us a way to glimpse the vast epochs over which the Milky Way has grown, changed and endured. And in this story, our own sun is a middle-aged character, quietly spinning in a spiral arm, part of a grand cosmic dance that stretches across space and time. Imagine the Milky Way as a sprawling city, alive with activity. The galactic centre is its bustling downtown, dense, bright, and chaotic, where stars crowd tightly together and energetic phenomena spark with intensity. Moving outward, the spiral arms are neighbourhoods filled with ongoing construction, fresh growth, and vibrant life. These are the regions where stars are born, where gas clouds glow, and where cosmic fireworks announce the life and death of suns. Now, consider where our solar system lies within this vast cityscape. We inhabit a quiet suburb, the Orion Spur, a relatively calm and stable stretch nestled between two larger spiral arms. It's a place of balance, far enough from the galactic core's bustle to avoid the hazards of intense radiation and crowded stellar traffic, yet close enough to benefit from the fertile materials needed to form stars and planets. This quiet neighbourhood may not have the flashy excitement of the galactic centre, but it offers something perhaps even more vital: stability. Our Sun and its planets orbit in a relatively peaceful zone where gravitational forces are gentle, and the frequency of nearby supernova explosions is low. This calm environment may be a crucial factor in allowing complex life to develop on Earth. In the denser inner regions, stars orbit faster and are packed more tightly, increasing the chance of gravitational disturbances. Such encounters can disrupt the delicate orbits of planets or expose them to intense bursts of harmful radiation. By contrast, the suburbs offer a gentler pace, a slower rhythm in which planetary systems can evolve undisturbed. The analogy of a city is apt in other ways as well. Just as a city's suburbs tend to be more spread out with quieter streets and open spaces, the Orion Spur is a minor arm, less dense and less active than the grander arms like Perseus or Sagittarius. It's not the busiest or brightest part of the galaxy, but it's where we live, where we thrive. Yet, quiet does not mean empty. Our neighbourhood hosts a variety of stellar phenomena, young stars shining brightly, remnants of ancient supernovae, and vast molecular clouds where new stars are born. It is a dynamic place, alive with change, but change on a timescale measured in millions or billions of years, a slow dance compared to the frenetic pace of the galactic core. Our solar system's position has been described as boring by some astronomers, a seemingly unremarkable spot in an unimaginably vast galaxy. But there is beauty in this ordinariness. It may be that this quietude is precisely what made Earth's rich tapestry of life possible. Far from dangerous stellar neighbours and cosmic storms, life could evolve slowly, uninterrupted by cataclysmic bursts. Consider the threats that come with being too close to the galactic centre or inside a dense star cluster. High-energy radiation, gravitational interactions, and the frequent deaths of massive stars as supernovae create a hazardous environment. Such regions may be inhospitable for life as we know it. Our suburban location, in contrast, offers a protective buffer, a cosmic safe zone where planetary systems can remain stable over billions of years. This perspective leads to a profound reflection. Perhaps our position in the galaxy is no accident. Maybe the Goldilocks zone extends beyond the habitable zone of a star, reaching out into the quiet suburbs of a galaxy where conditions favour the emergence and persistence of life. Astronomers continue to study the Milky Way's structure in exquisite detail, mapping not just the stars, but the swirling gas and magnetic fields that permeate space. This research reveals that our neighbourhood is shaped by both local and galactic scale processes, from spiral density waves that trigger star formation to subtle gravitational ripples caused by past encounters with smaller galaxies. Despite its seeming tranquility, the Milky Way is a living, breathing system. Its stars are born, live and die. Its arms twist and evolve, and its gravitational forces weave a complex web of interactions. Our solar system drifts through this cosmic city, caught in the rhythm of the spiral arms, moving quietly amid the ebb and flow of galactic life. When you gaze up at the Milky Way stretching across the night sky, you are looking inward, into the heart of this vast, ancient city. You're seeing the neighbourhood you call home, a place of calm amid cosmic commotion. In the grand scheme, our quiet suburb may seem small and unremarkable, but it is the stage on which the most extraordinary story unfolds, the story of life itself. When we think of the Milky Way, we often imagine a magnificent whirlpool of stars swirling gracefully through space in a cosmic dance. This elegant rotation is more than a visual spectacle. It is a dynamic system governed by the fundamental force of gravity. But as astronomers have observed the movements of stars within our galaxy, a puzzling truth has emerged. Something unseen holds the Milky Way together and keeps it spinning in a way that visible matter alone cannot explain. At first glance, one might expect stars farther from the galactic centre to orbit more slowly, just as planets in our solar system move slower the further they are from the Sun. Mercury races swiftly close in, while distant Neptune plods along at a leisurely pace. This pattern, governed by Newtonian gravity, would seem natural. Yet, when astronomers measured the speeds of stars and gas clouds at various distances from the Milky Way's centre, the results defied this expectation. Instead of slowing down, the stars in the outer reaches of the galaxy were found to orbit at nearly the same speed as those closer in, a phenomenon known as the flat rotation curve. This observation puzzled scientists because the visible mass, the stars, gas and dust we can detect with telescopes, simply didn't provide enough gravitational pull to hold these fast-moving stars in orbit. Without an unseen mass, they would fling out into intergalactic space. This mystery lingered for decades until the groundbreaking work of Vera Rubin, an American astronomer whose careful measurements of galactic rotation curves in the 1970s helped confirm that most of the galaxy's mass was invisible. Rubin's observations showed that galaxies, including our own Milky Way, are surrounded by vast halos of dark matter, a mysterious substance that neither emits nor absorbs light, yet exerts gravity just like ordinary matter. Dark matter is estimated to constitute about 27% of the universe's total mass-energy content, vastly outweighing the ordinary matter that makes up stars, planets, and everything we can see. It forms an enormous spherical halo enveloping the Milky Way, extending well beyond the visible disk, providing the gravitational glue that binds the galaxy's fast-moving outer stars. What exactly is dark matter? That remains one of the greatest enigmas in modern astrophysics. It might be composed of unknown particles, so-called WIMPs, weakly interacting massive particles, or something even stranger beyond our current theories. Despite its elusiveness, the evidence for dark matter's existence is overwhelming, shaping not only galaxies but the very large-scale structure of the cosmos. The presence of dark matter changes our understanding of the Milky Way, from a simple collection of stars to a complex system dominated by the invisible. Its gravitational pull sculpts the orbits of stars, dictates the formation of galactic structures, and influences how galaxies merge and evolve. This unseen mass allows the Milky Way's outer stars to maintain their speed, preventing the galaxy from flying apart. Without dark matter, the visible stars alone could not generate enough gravity to keep the galaxy intact. It's as if the Milky Way wears a cloak of invisible matter, spinning silently beneath the starlight. This discovery, that the majority of mass in galaxies is dark and unseen, marked a profound shift in our cosmic perspective. It revealed that much of the universe remains hidden from our senses and instruments, inviting both humility and wonder. Yet the galaxy story does not end with dark matter. Gravity leaves traces, clues that allow us to see the unseen, leading us to the next mystery. The Milky Way, vast and shimmering with stars, is but one piece of a grander cosmic tapestry, woven not only from the luminous matter we see, but also from an invisible web of gravity and mass. While dark matter remains elusive to direct detection, its presence is betrayed by one of the universe's most elegant phenomena, gravitational lensing. Imagine light travelling across the cosmos as a traveller on a highway. Usually it takes a straight path, moving undisturbed across the void. But when this light passes near a massive object, be it a star, a galaxy, or a cluster of galaxies, gravity acts as a detour sign, bending the path of light around the mass. This effect, predicted by Einstein's theory of general relativity, is called gravitational lensing. The effect is subtle, yet powerful. When a massive object lies between a distant source of light and an observer, the light is bent and focused, creating distorted, magnified, or even multiple images of the source. To an observer, a distant galaxy might appear stretched into arcs, duplicated, or ringed around the lensing mass in what is poetically called an Einstein ring. Gravitational lensing acts like a cosmic magnifying glass, allowing astronomers to study objects too faint or distant to be observed otherwise. But more importantly, it reveals the mass distribution of the lensing object, including the unseen. Clusters of galaxies, the largest gravitationally bound structures in the universe, often act as lenses. By analysing the distortions in background galaxies caused by these clusters, astronomers can map the total mass of the cluster, both the visible matter and the dark matter. This technique has shown time and again that the visible matter, stars, gas, dust, accounts for only a fraction of the total mass needed to produce the observed lensing effects. The rest must be dark matter, invisible but gravitationally potent. In the Milky Way, gravitational lensing helps us peer into the dense galactic centre and detect otherwise hidden objects, such as rogue black holes or compact dark matter clumps. On a grander scale, the cosmic web, a vast network of filaments composed of dark matter and gas, forms the scaffolding upon which galaxies and clusters assemble. This invisible skeleton stretches across the observable universe, with galaxies forming along the dense knots where filaments intersect. Between these filaments lie enormous voids, regions nearly empty of galaxies and matter, a haunting contrast to the luminous threads. Understanding this dark skeleton is akin to tracing the architecture of an unseen building by watching how light bends around its corners. Through gravitational lensing, the universe offers a glimpse into its invisible framework, a framework that governs the formation and evolution of galaxies, including our own Milky Way. While the concept of an invisible pervasive mass may seem abstract, gravitational lensing grounds it in observation. The cosmos speaks through the bending of light, whispering secrets about what lies beneath the starlit surface. This understanding reshapes our view of the universe, transforming it from a simple collection of stars and galaxies into a dynamic, complex web of matter and gravity, much of it hidden, but all of it essential. As we continue our journey, we turn from the invisible mass that holds galaxies together to the mysterious magnetic fields that thread through them, subtle forces shaping the cosmic weather and whispering tales of the galaxy's unseen currents. When we imagine the forces that shape galaxies, gravity often takes centre stage, the relentless sculptor pulling stars, gas and dust into majestic spirals and dense clusters. But the Milky Way is more than just gravity's playground. Woven throughout its vast expanse is another subtler force, magnetic fields. Invisible yet powerful, these magnetic fields thread through the galactic disk, halo, and spiral arms, influencing the motion of charged particles, guiding the paths of cosmic rays, and playing a quiet but vital role in the birth and death of stars. Magnetic fields in galaxies are not easy to detect. Unlike stars that shine with a light visible to our eyes, magnetic fields are intangible. We infer their presence through the effects they produce, by observing how they polarize light, or by the radio waves emitted by high-speed electrons spiraling along magnetic lines in a phenomenon called synchrotron radiation. In the Milky Way, these fields stretch over tens of thousands of light years. Their strength, while weak compared to the magnets we use in everyday life, is significant on cosmic scales. They influence the behaviour of the interstellar medium, the gas and dust filling the space between stars, shaping the clouds from which new stars will eventually emerge. Picture a vast invisible latticework, like a web of silk threads stretched across the galaxy, holding and guiding the motions of charged particles and influencing the flow of gas. This magnetic weather affects how gas clouds collapse, how cosmic rays propagate, and how energy moves through space. These fields also protect star systems like our own by deflecting high-energy particles and cosmic rays that might otherwise strip away planetary atmospheres or pose hazards to life. Earth's own magnetic field is a local echo of these grand galactic patterns, a microcosm of magnetic protection. Yet, despite their importance, many aspects of galactic magnetic fields remain mysterious. How are they generated? Are they primordial, born from the earliest moments of the universe? Or have they been amplified over billions of years by the galaxy's rotation and turbulence in the interstellar medium? Theorists propose dynamo mechanisms, processes by which weak seed fields are strengthened by the swirling motions of ionized gas. These magnetic fields can wax and wane, twist and tangle, influenced by galactic collisions and star formation. Sometimes magnetic fields channel flows of charged particles into spectacular jets from the centres of galaxies. Though our Milky Way's central black hole is relatively quiet, other galaxies blaze with magnetic-powered outflows, stretching light years into space. Within the spiral arms, magnetic fields help organize the complex motions of gas clouds. They can slow the collapse of these clouds, regulating the pace of star formation and shaping the distribution of newborn stars. In a way, they act like galactic weather patterns, guiding storms of gas and dust across the galaxy's landscape. This galactic weather is dynamic. Magnetic fields can shift and evolve, interacting with cosmic rays and turbulent flows. This interplay influences everything from the birth of stars to the propagation of energetic particles that eventually reach Earth. Modern radio telescopes and space missions continue to study these magnetic whispers. The polarized light they measure allows astronomers to map the invisible lines threading through the galaxy, revealing patterns and structures that challenge our understanding. Reflecting on these invisible forces invites a kind of quiet wonder. The Milky Way is not a static, inert collection of stars, but a living, breathing system. Gravity is its architect, but magnetic fields are the gardeners, shaping, nurturing, and sometimes restraining the growth of stars and planets. In the gentle hum of these magnetic winds, we find another dimension of cosmic complexity, another layer of mystery, and another reminder that much of the universe's beauty lies in what we cannot see. As we close this chapter, we prepare to look beyond these invisible forces to the restless life of the galaxy, its collisions, births, and cosmic rays, in the next part of our journey. Imagine a vast ballroom stretching across millions of light years, where immense dancers glide in slow motion. Their steps are measured not in seconds, but in millions of years. These dancers are galaxies, colossal collections of stars, gas, dust, and dark matter, each one a universe unto itself. And like dancers, galaxies do not move in isolation. They are drawn to one another by gravity's unyielding embrace, their paths intertwining in a slow, swirling dance that shapes the cosmos. Our Milky Way is no exception. It has spent billions of years growing and changing through encounters and collisions with smaller galaxies. Far from the violent crashes one might imagine, these interactions often unfold over vast spans of time, gentle gravitational pulls pulling in stars and gas, blending them into new forms. One of the most compelling pieces of evidence for this history is the presence of stellar streams, long, thin trails of stars that arc across the sky, remnants of galaxies and star clusters torn apart and absorbed by the Milky Way's gravity. These streams are like cosmic breadcrumbs, left behind by swallowed companions. Among the most notable is the Sagittarius dwarf galaxy. Discovered in the 1990s, it is a small satellite galaxy caught in the Milky Way's gravitational grip, slowly being pulled apart. Its stars stretch out in vast tidal streams, weaving through the halo of our galaxy. Over the coming billions of years, it will be fully assimilated, its stars becoming part of the Milky Way's grand population. Thanks to the precision of the Gaia spacecraft, astronomers have been able to map these stellar streams with unprecedented clarity, revealing the remnants of past mergers and the complex structure of the galactic halo. Gaia's data shows that the Milky Way has absorbed not just the Sagittarius dwarf, but multiple smaller galaxies in its history. These ancient encounters have left their mark in the motions and chemical signatures of stars scattered across the halo. Each merger is a chapter in the Milky Way's biography. When a smaller galaxy approaches, the gravitational forces tug on the gas and stars, sometimes triggering bursts of star formation as clouds compress and collapse. This cosmic recycling helps build the spiral arms and enrich the galaxy with heavier elements, carbon, oxygen, iron, forged in the hearts of massive stars. Though slow, these mergers are transformative. They can distort the shape of the galaxy, warp its disk, and send ripples across its structure. The Milky Way's somewhat warped and lopsided disk may be a result of such past collisions, evidence that the galaxy is a dynamic, evolving entity. far from being a static, isolated island in space, our galaxy is part of a rich ecosystem, a family of galaxies known as the Local Group, including the Andromeda Galaxy and the Triangulum Galaxy, as well as dozens of smaller companions. Over billions of years, these galaxies interact, dance and merge in an intricate cosmic choreography. In about 4 billion years, the Milky Way and Andromeda will engage in one of the grandest dances yet, a collision that will eventually merge the two into a single larger galaxy. This slow-motion event will dramatically reshape the local cosmos, although the vast distances between stars mean that direct stellar collisions will be rare. These galactic mergers remind us of the universe's ongoing creation, a slow, majestic process that unfolds on scales far beyond human lifetimes. They show that galaxies are not fixed sculptures but living, breathing entities that grow, change and evolve through interaction. In this cosmic dance, the Milky Way's arms, bulge and halo are the sum of billions of years of encounters, each one adding to the rich tapestry of stars we call home. So when you look up at the night sky, remember, you're witnessing the aftermath of ancient embraces, the gentle blending of galaxies, and the slow unfolding of a story billions of years in the making. Before the Milky Way existed, before stars ignited, before even atoms gathered, there was the universe, a silent, dense, and unimaginably hot expanse. This was the beginning of all things, the moment when time, space, and matter emerge from a state beyond our understanding. Scientists call this moment the Big Bang, a cosmic event that occurred approximately 13.8 billion years ago. Though the phrase Big Bang might conjure images of an explosion, a sudden, violent blast, it was more of a rapid expansion of space itself. Imagine a balloon inflating, but at speeds faster than light, carrying with it everything that would ever exist. Space stretched, cooled, and transformed, allowing the first particles to combine into the simplest atoms, hydrogen and helium. For hundreds of thousands of years, the universe was a glowing fog of particles and radiation. Then, in a moment called recombination, atoms formed stable structures, and light, previously trapped and scattered, began to travel freely. This ancient light, now cooled to microwave frequencies, still fills the universe. It is known as the cosmic microwave background, CMB, the faint, all-pervading glow that is the universe's baby picture. The CMB carries subtle patterns, tiny fluctuations in temperature and density, that whisper the earliest stories of cosmic structure. These fluctuations, mere ripples in a vast ocean, were the seeds from which galaxies would grow. To explain these early conditions, scientists developed the theory of cosmic inflation. Inflation posits that in a tiny fraction of a second after the Big Bang, the universe expanded exponentially, smoothing out irregularities and stretching quantum fluctuations into the large-scale structures we observe today. It is a theory that blends the smallest scales of quantum physics with the grandest scales of cosmology. But the universe is more than what we see. Observations reveal that ordinary matter, the atoms that make up stars, planets, and ourselves, accounts for only about 5% of the total content of the cosmos. The rest is composed of dark matter and dark energy, mysterious components that govern the universe's evolution and fate. Dark matter, as we discussed earlier, acts as a gravitational scaffold, pulling matter together to form galaxies and clusters. Dark energy, on the other hand, is driving the accelerated expansion of the universe, pushing galaxies apart with a force we barely understand. The universe is, in a sense, a delicate balance between these forces, attraction and expansion, light and darkness, simplicity and complexity. From the quantum jitters in its earliest moments to the swirling galaxies that grace the night sky, the cosmos has blossomed in both scale and richness. Galaxies like the Milky Way are the fruits of this cosmic bloom. They formed where dark matter halos, gathered enough ordinary matter to ignite star formation. Over billions of years, gravity wove the gas and dust into stars, clusters and spirals. Studying the CMB and distant galaxies through telescopes like Planck and WMAP allows us to peer back in time, watching the universe's infancy and youth. Each photon of light that reaches us from distant galaxies is a messenger from the past, carrying information about the conditions when the cosmos was young. The story of the universe's beginning is both scientific and poetic. It is a tale of emergence from simplicity to complexity, from darkness to light, from chaos to order. And it is a story that continues to unfold with every new observation, every new theory, every new moment of quiet wonder beneath the stars. As you lie back and let these thoughts drift through your mind, you become part of this vast unfolding, a small but essential note in the symphony of cosmic history. As we gaze peacefully at the stars, it's easy to imagine space as serene and silent, a quiet expanse stretching endlessly between the glowing points of light. Yet the cosmos is far from still. Invisible to our eyes, a storm of particles races through the galaxy at near the speed of light. These are cosmic rays, high-energy travellers born in the most violent and energetic places in the universe. The story of cosmic rays begins in the early 20th century, when Austrian physicist Victor Hess took to the skies in a balloon to investigate an odd phenomenon. Scientists had noticed that radiation levels seemed to increase at higher altitudes, contrary to the expectation that Earth's surface would be the most irradiated. To solve this mystery, Hess ascended nearly 5 kilometres above the Earth's surface, with instruments to measure ionising radiation. His daring flights in 1912 revealed a surprising truth. Radiation was not only coming from Earth, but also from space. This discovery opened the door to a new understanding of the universe's energetic processes. Cosmic rays are primarily composed of protons, the nuclei of hydrogen atoms, but also include heavier atomic nuclei such as helium, carbon and even iron. These particles are accelerated to incredible energies, travelling through the galaxy and beyond, constantly bombarding Earth and everything in it. But where do these cosmic bullets come from? The leading sources are the remnants of supernovae, the explosive deaths of massive stars. When a star runs out of fuel, its core collapses, triggering a spectacular explosion that can briefly outshine entire galaxies. These shock waves propagate through space, accelerating charged particles through a process known as Fermi acceleration. Magnetic fields twist and tangle, whipping particles into near-light speeds. Beyond supernovae, some cosmic rays are thought to originate from even more extreme environments, such as the powerful jets emitted by active galactic nuclei or the turbulent regions near black holes. The Fermi Gamma Ray Space Telescope, launched in 2008, has helped confirm many of these sources by observing gamma rays emitted as cosmic rays interact with gas and radiation. As these particles speed through the Milky Way, they do not travel in straight lines. Galactic magnetic fields, those invisible threads we spoke of earlier, weave a tangled web that bends and twists their paths, causing cosmic rays to bounce and spiral. This random walk makes it difficult to trace any single particle back to its origin, adding a layer of mystery to their journeys. Cosmic rays are more than astrophysical curiosities. When they reach Earth, they interact with the atmosphere, producing showers of secondary particles that influence cloud formation and may affect the climate. For astronauts venturing beyond Earth's protective magnetic field, cosmic rays pose significant radiation hazards. Understanding their nature and origin is vital for future space exploration and long-duration missions. Among cosmic rays, a special class stands out: ultra-high-energy cosmic rays, particles so energetic that their origins remain enigmatic. These rare travellers carry energies millions of times greater than those produced by human-made particle accelerators. They may come from distant galaxies hosting supermassive black holes, or from exotic phenomena yet to be fully understood. In a way, cosmic rays are messengers, remnants of violent processes that shape the galaxy and continue to sculpt the universe. They remind us that even in the vast quiet between stars there is motion, energy, and a restless vitality. So while the night sky may look peaceful from Earth, it is in truth a stage for invisible storms and radiant journeys. Every moment, countless cosmic rays pass through your body, silent travellers from distant cataclysms, linking us intimately to the ongoing drama of the cosmos. As we continue our voyage, we leave these energetic travellers behind to delve into the profound silence and subtle signals of the universe, the quiet mysteries that await our discovery. If the Milky Way is brimming with billions of stars, many of which host planets, some perhaps harbouring life, then why, when we listen carefully, do we hear only silence? This question, famously posed by physicist Enrico Fermi in the mid-20th century, resonates through the quiet void between stars. Where is everybody, he asked, not as a rhetorical flourish, but as a profound challenge to our understanding of life in the cosmos. The Fermi Paradox highlights a startling contradiction. On the one hand, given the vast number of stars and potentially habitable planets, the universe seems likely to be teeming with life. On the other hand, despite decades of searching, no clear signs of extraterrestrial civilizations have been found. No radio signals, no spacecraft visits, no technological footprints. To make sense of this paradox, scientists have formulated tools to estimate the number of detectable civilizations in our galaxy. One of the most well-known is the Drake equation, developed in 1961 by astronomer Frank Drake. This equation multiplies together several factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction that evolve intelligence, the fraction that develop technology, and the length of time such civilizations release detectable signals. While the equation offers a framework, it is laden with uncertainties. Each factor is a guess, some based on limited data, others deeply speculative. Depending on the values chosen, the equation can predict anything from a galaxy bustling with civilizations to one utterly alone. Among the many possibilities to explain the silence is the idea of the Great Filter. This hypothesis suggests that somewhere along the path from simple molecules to advanced, spacefaring civilizations there is a bottleneck, a stage that is incredibly difficult or unlikely to surpass. This filter might be behind us, meaning that the emergence of complex life or intelligence is rare, or it might lie ahead, implying that civilizations tend to self-destruct before achieving long-term survival or interstellar communication. The Great Filter presents a sobering reflection on the fragility of life and technology. It invites us to consider our own future carefully, acknowledging that the cosmic silence might not be due to lack of company, but the rarity of enduring. Despite the mystery, the search continues. The search for extraterrestrial intelligence, SETI, is an ongoing effort to detect signals or signs of other civilizations. Using large radio telescopes, scientists scan the skies for patterns that might indicate artificial origin, narrowband signals, repeating pulses, or unusual modulations. So far, SETI has not confirmed any unambiguous signs, but the search covers only a fraction of the galaxy and a tiny window of time. This silence does not discourage but inspires humility and curiosity. It reminds us that the cosmos is vast, our methods limited, and the answers may lie beyond current technology or understanding. It also opens philosophical questions about the nature of intelligence, communication, and the likelihood of coexistence. Are civilizations common but silent? Do they communicate in ways we cannot yet detect? Or is the universe genuinely quiet, save for our solitary whispers? As you consider these questions tonight, you join a long line of thinkers who have looked up with wonder and sought to understand not just the stars but the spaces between them, the silence, the mystery, and the possibility. The question, where is everyone, is not just a query but an invitation to keep listening, to keep searching, and to cherish the profound mystery that connects us to the cosmos. The night sky holds countless stars, and around many of those stars circle worlds of all sizes and varieties. Over the past few decades, astronomers have discovered thousands of these exoplanets, planets beyond our solar system, opening a new chapter in humanity's quest to understand whether life exists elsewhere. Exoplanets come in astonishing diversity. Some are gas giants many times the size of Jupiter, blazing hot as they orbit perilously close to their suns. Others are small, rocky worlds like Earth, orbiting in the habitable zone, the sweet spot where temperatures could allow liquid water to exist. Water, the essential solvent of life as we know it, has become a guiding beacon in the search for habitable environments. Detecting these distant worlds is no simple feat. Many methods exist, from measuring the tiny dip in a star's brightness when a planet crosses in front, known as a transit, to observing the subtle gravitational tug planets exert on their stars called radial. Velocity instruments like NASA's Kepler Space Telescope and its successor, TESS, have revolutionized our ability to find these elusive planets, revealing that planets are common throughout the galaxy. But finding planets is only the beginning. Scientists seek signs of life by studying biosignatures, atmospheric gases like oxygen, methane, or combinations that could hint at biological processes. Upcoming telescopes, such as the James Webb Space Telescope, aim to analyze exoplanet atmospheres with unprecedented detail, searching for these subtle fingerprints. Yet, as we expand our view of habitability, life itself challenges our assumptions. On Earth, life thrives not only in temperate forests or oceans, but also in extreme environments once thought uninhabitable. Microorganisms called extremophiles flourish in boiling hot springs, frozen tundras, acidic lakes, and crushing depths. These hardy survivors stretch the definition of where life can exist. If life on Earth can endure such extremes, then the universe's possibilities may be broader than once imagined. Planets orbiting dim red dwarf stars, once dismissed as too volatile or prone to radiation, now present potential niches for life, especially if protected by magnetic fields or subsurface oceans. The variety of possible alien worlds is staggering. Some may be rocky, with thin atmospheres and barren landscapes. Others may be ocean worlds, enveloped in deep water beneath thick ice shells. Still others could be gas dwarfs with dense atmospheres, or exotic worlds with compositions unknown on Earth. While we have yet to find direct evidence of life beyond our planet, the rapidly growing catalogue of exoplanets provides hope and inspiration. Each discovery is a whisper that life could exist elsewhere, not just as simple microbes, but perhaps as complex organisms, even intelligent beings. As we ponder these possibilities tonight, it is humbling and exhilarating to realize that Earth is part of a vast family of worlds. The search for life is no longer the stuff of science fiction. It is a scientific endeavor rooted in careful observation, deep curiosity, and profound respect for the unknown. We do not yet know what alien life might look like, or whether it communicates or even understands the universe as we do. But the quest to find it enriches our appreciation of life's resilience and creativity, and reminds us of our shared origins in the star stuff of the cosmos. So, as you lie beneath the stars, imagine the countless worlds that circle their suns, each with its own story unfolding. Imagine the silent possibilities, the hidden oceans, the spark of life waiting patiently in the dark. The universe is not only vast in space but rich in potential, a garden of worlds blooming beyond the reach of our eyes, inviting us to explore, to wonder, and to dream. The universe stretches vast and silent before us, filled with countless stars and potentially billions of worlds. Yet the profound question remains, why, amid this cosmic abundance, have we not heard a whisper from another civilization? This silence invites us to explore not only the possibilities of life, but also the reasons why the stars might remain quiet. One intriguing idea is the zoo hypothesis, the suggestion that advanced extraterrestrial civilizations are aware of us, but intentionally avoid contact. Like vigilant observers watching animals in a nature reserve, these civilizations might choose to keep their presence hidden, allowing younger, less developed species like ours to evolve naturally, undisturbed by outside influence. In this scenario, the silence is not absence, but a deliberate choice, a cosmic courtesy or quarantine. Another thought-provoking theory is the dark forest hypothesis, which paints the universe as a dark and dangerous place. In this view, every civilization is a hunter, hiding quietly to avoid detection. Revealing one's location could invite destruction, as others might perceive new voices as threats. The silence becomes a survival strategy. Civilizations stay hidden, communication is minimal, and the cosmos remains a shadowy forest where everyone listens carefully and shoots first. These ideas remind us that silence need not mean loneliness. It could be a sign of caution, wisdom, or strategic restraint. Perhaps our own broadcasts, limited and brief, have not yet reached ears that are listening carefully. Or perhaps they are purposefully ignoring the noise of fledgling civilizations. Yet another possibility lies in the limitations of our technology and understanding. Our current methods, such as scanning for radio signals, might miss communications based on different frequencies, encryption methods, or even entirely different technologies we cannot yet imagine. Civilizations might communicate through means beyond our detection, or exist in ways we cannot yet comprehend. Time, too, plays a role. The galaxy is nearly 14 billion years old. Civilizations may arise and fall separated by millions of years, never overlapping long enough to meet. We could be early or late in this cosmic timeline, isolated simply by circumstance. These hypotheses, while speculative, offer valuable reflections on our place in the universe. They encourage humility and open-mindedness, reminding us that the absence of evidence is not evidence of absence. As we reflect on these possibilities tonight, the cosmic silence transforms from a void into a space filled with quiet potential. It invites us to listen deeper, to search wider, and to appreciate the vast mystery that envelops us. Perhaps the universe's silence is a lullaby, a gentle hush before new voices arise, a soft space for dreams to unfold, and an invitation for us to become better listeners. Since the dawn of the space age, humanity has sent instruments aloft to orbit the Earth and peer back at the planet that gave us life. Among the pioneers of this, Celestial Watchtower was the Landsat program, beginning in 1972, a series of satellites designed not just to take pictures, but to observe, record, and understand the dynamic changes unfolding across Earth's surface. Landsat's cameras do more than capture images. They measure the reflected light across multiple wavelengths, visible, infrared, and beyond, creating rich data sets that reveal the health of forests, the extent of ice, the growth of cities, and the shifting patterns of agriculture. These satellites provide a gentle but persistent gaze, a continuous diary of Earth's transformations. Over nearly 5 decades, Landsat has chronicled some of the most striking changes our planet has experienced. The once vast Aral Sea, nestled in Central Asia, has shrunk dramatically due to water diversion and climate change. Its exposed bed a haunting testament to human impact. The Amazon rainforest, often called the lungs of the planet, has seen extensive deforestation, a process carefully tracked from space, revealing both the damage and the areas spared by conservation efforts. Even the silent retreat of glaciers, some so remote they defy easy study from the ground, has been monitored from orbit, offering critical data about rising temperatures and sea level changes. Urban areas too have expanded, their glowing footprints visible in nighttime satellite images, a mosaic of human settlements spreading inexorably across continents. This remote sensing capability has revolutionized how we understand Earth as a living system. It is no longer just a collection of separate countries and ecosystems, but a connected whole, where changes in one region ripple across the globe. The satellites watch patiently, without judgment, chronicling the delicate balance of air, water, land, and life. The data from these eyes in the sky inform scientists, policymakers, and conservationists, guiding efforts to protect the planet and sustain its resources. They help forecast droughts, monitor natural disasters, and map deforestation in near real time. In many ways, this quiet observation has become a lifeline, a means to know Earth better so we might care for it more wisely. Yet, beyond the science and policy, there is a profound shift in perspective that comes with seeing Earth from above. The planet transforms from a patchwork of borders and disputes into a fragile glowing orb, suspended in darkness. This vantage invites reflection on our shared home, its beauty and its vulnerability. The Landsat satellites and their successors offer us a mirror. They remind us that the Earth is a dynamic place, constantly changing, alive with movement and interaction. They invite us to watch not just with eyes, but with understanding and care. Tonight, as you listen, you might imagine these satellites silently circling day and night across the heavens, a quiet vigil for a planet spinning beneath the vast starlit sky. Imagine drifting gently above the Earth, looking down on a vibrant blue globe swirling slowly against the black velvet of space. From this extraordinary vantage, the world appears as a whole, fragile, luminous, and breathtakingly beautiful. It is a view that has changed the lives of countless astronauts, forever altering the way they think about our planet and our place within it. This profound psychological shift is known as the overview effect. Coined by space philosopher Frank White in the late 1980s, the overview effect describes the transformative experience reported by those who have seen Earth from orbit or beyond. For many astronauts, the sight of our planet, the seamless unity of oceans, continents, clouds, and life, evokes a deep sense of connection, humility, and responsibility. It is as if the borders and divisions we take so seriously on the ground dissolve into insignificance when viewed from space. Take, for example, astronaut Edgar Mitchell, the 6th person to walk on the moon. He described his experience as a sudden awareness of Earth as a tiny blue and white jewel, a lonely speck in the vast enveloping cosmic dark. This realization, he said, sparked a profound spiritual awakening, a sense that all humanity shares a common home deserving of care and respect. Similarly, Canadian astronaut Chris Hadfield spoke of the overwhelming beauty and vulnerability of Earth, seen from the International Space Station. He noted how the thinness of the atmosphere and the delicate patterns of weather systems highlight the planet's fragility. From space, Earth is a precious oasis, suspended in the void. The overview effect often instills a feeling of global unity. Astronauts report how nationalities and political boundaries become meaningless. They feel connected not just to their fellow humans, but to all life on Earth. This shift can inspire new values, environmental stewardship, peace, and a sense of shared destiny. Interestingly, this psychological transformation is not limited to astronauts alone. People who experience simulations of the overview effect through virtual reality or immersive films also report feelings of awe, humility, and a desire to protect the planet. This suggests that the effect taps into a deep human capacity for perspective and empathy. From a scientific standpoint, the overview effect can be linked to changes in brain function when confronted with overwhelming beauty and new perspectives. It engages areas responsible for self-reflection, emotional processing, and awe. This interplay of cognition and emotion encourages a rethinking of one's place in the universe. Yet, the effect also carries a bittersweet note. Along with awe comes the stark awareness of environmental threats, climate change, habitat loss, pollution, visible even from space. This duality of beauty and vulnerability can motivate action, but also provoke a sense of urgency and melancholy. Reflecting on the overview effect invites us to consider how perspective shapes understanding. The view from space reveals connections that are invisible from the ground. It reminds us that Earth is not just a collection of nations or ecosystems, but a single living system, delicate and interconnected. As you listen tonight, imagine floating gently in orbit, seeing the blue planet turn beneath you. Imagine the quiet that follows, the hum of life, the swirl of clouds, the glint of city lights. Let that image settle softly in your mind, carrying with it a sense of belonging and responsibility. The overview effect offers a quiet invitation to look beyond the immediate, to see the whole, and to cherish the small and precious world we call home. As our journey through the Milky Way nears its quiet close, imagine once more the vast spiral of stars stretching across the night sky. This spiral is ancient and immense, composed of billions of suns, swirling gracefully in an eternal slow dance. We, perched on one modest arm, are carried by this gentle turning, part of a cosmic rhythm that stretches beyond our comprehension. The galaxy's spiral arms curve like delicate ribbons, tracing paths carved by gravity and shaped by unseen forces. They're corridors of birth and death, where clouds of gas condense into glowing stars, and where those stars eventually expire, seeding the galaxy with the elements of life. Each turn of this spiral carries with it the echoes of those processes, a rhythm older than humanity, older than Earth itself. Within this vast motion lies a story of belonging. The atoms in your body, the carbon in your cells, the calcium in your bones, were forged in the hearts of stars long vanished. They travelled across space and time, woven into the fabric of this galaxy's spiral, only to become you. To be part of this galaxy is to be connected to its ancient light and shadow, its quiet power and ceaseless change. We have explored mysteries hidden in darkness, the black hole at the centre, the dark matter holding the galaxy's shape, the magnetic fields whispering through interstellar clouds. We have listened to the stories of cosmic rays racing between stars and pondered the profound silence that fills the spaces where we might have expected voices. Tonight, as you let your thoughts drift like stardust in the galactic breeze, consider the quiet dignity of the Milky Way. It does not shout its presence. It does not hurry or falter. It moves with steady grace, carrying its billions of stars and their planets, and us, through the darkness. This gentle turning is a lullaby for the cosmos. It reminds us that motion does not have to be loud or frantic to be profound. The slow spiral, the steady orbit, the soft pulse of light across distances unimaginable. These are the rhythms that sustain the universe. As you prepare to rest, allow the image of this spiral to settle in your mind's eye. Imagine the stars as gentle guides, spinning softly in the velvet night, inviting you into their endless journey. Sleep well, little traveller within the spiral. Know that you are part of something vast and ancient, quietly turning through time and space. The galaxy carries you gently, like a lullaby sung across the stars. And when dawn comes, or when your dreams begin, remember this: the spiral moves on, steadfast and serene, and so do you.